PyCon is happy to. I'm happy to be here. I'm Thomas. I'm a machine learning engineer since 3 years. Before that, I was studying bachelor and masters. All of these I studied with the focus on machine learning and AI. This is not a topic about AI. It's about like the bare bone performance of Python. So, first of all, you might think, okay, why is Python performance important? Or how do you measure it? So, before I go more in depth about what the talk is about, I will briefly give you an example of what the talk is not about. So the talk is not about hacking code in Cython. The talk is not about comparing different interpreters, so like Cython, PyPy, or Rust Python, or using like external libraries to optimize your Python code, like Numba or Desk. So this talk is really simple, pure simple Python, mostly based on the standard library. What are the mini optimization you can do to improve your quality and the speed of your code? So, most people don't think like Python is like a fast language if you compare it to like a statistical type language like Rust or JavaScript. But Python is coming really far good along with each version increases. You see on the bar chart of Python, with each version increases from Python, the speed of the Python execution goes a little bit better and better and better. So like the best performance increase in the last time was the jump from version 3.10 to 3.11. So if you can really keep my talk short, it might be sufficient enough to upgrade your Python version on your legacy project to gain like a significant performance. So this is something you can also read about. I will later post the slides, and I will link a blog post where this graph chat is from, and this goes in why Python has such a steady increase in performance over each version. So now we go into like the optimization part. Before I want to go into the optimization part, I want to use the speech of Donald Knuth. Donald Knuth is a famous informatiker. He said premature optimization is the root of all evil. And down there is under the headline is the full quote. And like the really important stuff with optimization your Python code, which I then later will show you how it's done, is that you really should be aware that you don't go too far into the detail and spend like your whole time only to optimizing your code you have already written, and not focusing on writing like a new features, a new product, or like do feature optimize or program new features. So now, before we can go into the optimization, we first of all need to look at how our code is performing, so that we don't end up like here Donald Knuth said in the quote. So, and therefore, you need to have some mechanism of profiling. So a profiler is simply put like a way to analyze how performant your code is running. So the tools which I use now for the talk is the timed module in the C profile model. Both of these are quite are in the standard library and are easy to use. If you want to analyze like a larger code base or like production-ready systems, there are also other profilers you can use, or also inline profilers, but I condense this talk down to these two profilers. And it's always important for you to measure your code or you measure your optimization, because you're trying to optimize. If you optimize your code, you're trying to optimize on bottlenecks of your code. So you can optimize like your whole code, but it's like a never-ending task, because there are small screws which you can tighten and which makes it faster, but mostly on the readability or like it takes a lot of time. So I will show you now what C profiler is. As I already said, C profile is the built-in Python module for profiling code. It's based on C under this function of Python, and it provides you a detailed information how the execution time of your program or like of your function is called and how much time it did take to compute. So the code is quite simple. You only need to import C profile, then have a function. Here, here I have simply an example function, and then you can simply call like the C profile model with the run function and give over like the function you try to optimize or you try to analyze. This can also be like your main function. So how does it look like then in general? So if you run the code, you get like then this output, which says how many function calls were in the function you provided, and which function structure did take how much time. This is the first column, the second column, total time, and like the third column is the cumulative time of the execution of all of that. And this builds here in C profile the call structure of your function you're calling and gives out how much time you did spend for like each function call inside the function. So this is sufficient enough to get like an overview of like your normal Python optimization or how your function is running comparatively. But if you want to have something in production, it might be worth to consider like a line profiler that you can use. So the next step, if you have your profiling done, is that you need to plan your optimization. The key adjectives therefore is measure, target, optimize, validate. So first of all, you measure what you want to optimize. This can therefore you can use like timeit or C profile to look if this really is a bottleneck in your code. This function or this code snippet you're providing, or like in general. So then you need to identify what is really the bottleneck. Is the bottleneck really on the performance side, so CPU, or is this on the memory side, or on the input-output operations like disk speed or like network interfaces? And then you can apply the optimization in the third step, only in the third step. So before that, you need to make sure it's really an issue, and you also need to make sure that you can fix the target and don't optimize like the CPU performance if like memory speed is the issue. So it won't help you further. And then if you've done your optimization, you can validate. So, and to hammer further this point, this is XKCD comic about how much time you can spend optimizing your function code. And this is why I really want to hammer it in, that before you're doing your optimization, please reconsider if it's really a bottleneck in your performance. It's really the bottleneck you want to address, or it's simply like a micro optimizations. Because you can use a lot of time to optimize your code. So if now we have like the profiling done, I want to get into like the detail how you can optimize now in Python. So in Python, it's really important to choose the right data structure. So choose the right data structure. So for example, like lookups, comparison can be faster and with a different data structure. So like here in the example, an immutable tuple is faster than a list in Python to execute and search. The data performance increase is really not that large. This is more like a micro optimization, which you can consider it while writing the code, but I wouldn't change this on like a production-ready code basis. The next point is something which also is about like more about types. It's how you string concatenate. Here, in the example, you can see like we are trying to concatenate strings from our list, and like normal way you might learn is in the don't line and the line 10 to plus operate in the line 11 to plus to concatenate with a plus inside of loop. And this is something which is really bad in Python because like the string data type in Python is immutable. And every time you call the assign function to a new string, you need a new memory allocation, and this takes really time, and therefore it's really better to use built-in methods like in the line 5 with join, where you can simply join the list up in parts. So this can be quite helpful if you're trying to have. Oftentimes this is an issue in production-ready code because this adds up if in a long loop. So the other things I want to also to show you about is really using like the standard built-in function in Python. So Python has really lots of cool functions like sum, map, filter, or sort, which are mostly implemented in C and are really fast. And so if you compare it with like a normal algorithm, or if you don't use it, it adds, the performance adds. So here, the performance increase isn't that large because we try to map like the map generator back to a list, and this is something which takes a lot of time in Python. But otherwise, this would be like outside of this example case, a really good use to use this utilization of like the normal functions. So, also, I showed you a list comprehension as a second example. Please be aware that list comprehension without external function calls can be extremely fast. The performance tanks only if you really call like external functions, and if you have like a huge call stacks. Otherwise, list comprehensions are really a good way to optimize your code. I wouldn't dare to say that you should only write list comprehension because sometimes, or sometimes they can be a bit too heavy if they and not easy to maintain if they are too large or have too much stuff in it. So the other thing I wanted to show is like a feature most of you might not know. It's the Python function, it's the Python cache from functools. So the LAU cache is a simply least recently used cache, And if the function is called with like a parameter, then you can, a cache is saved. And if you call the function again with the same parameter, it simply uses the cache version of it. This is a really easy to implement change because you can use like the LRU cache decorator. So this can be a considerable speed increase as shown below if the function calls has always the same parameters. Our caching mechanism is good. So this is something you can also easily add to your code. So I think this were lots of little micro-optimizations pattern I showed you. Now I want to be a more generalized with that. So I want to speak about the pitfalls and any patterns of optimization. So as I already discussed in the beginning, over-optimization can hurt the readability and the maintenance, and it also takes a lot of time. This is why you should focus only really on your bottlenecks and try to optimize your bottlenecks. Most likely, it's one or two lines of code which are really the issues, which are either like a unnecessary nested loop, which you can simply remove, or something like that that you can optimize. So also be aware that like the concurrency of your CPU and the input and output concurrency can be different. So therefore, try really to optimize on, if you know it, like CPU is a problem, try to optimize on that and not on there. So, and the other thing, the third point is really, if you profile, misinterpretation can happen. So therefore it's always good to correlate like the results of your profiling with what your real world use cases would be. Normally you don't write like at the beginning of your project like a system that can scale up to 2 million users. So normally you start quite small and then do this, or that do like the profiling and the optimizing if like problems arises in the performance. And you should always balance the optimization and the performance gain with code clarity and maintainability, because like code clarity and maintainability is like the stuff which helps you in the long run, and you can, because otherwise you can really destroy your code readability if you're trying to micro-optimize your code. So I had the pitfalls, and now what are the best practices for optimization? So as I already said, profiling before optimization. Use built-in or well-tested libraries so that you can certain that the functions are already good maintained. This is also good use cases why we can use like the built-in standard library functions, because normally they are already quite optimized at sea level. And if you change in your code, if you change something in your code, try to condense it really at like small local changes to really comprehend if like the change you did really improved like the performance, or if it has some side effects you didn't consider the first time. And if you do like lots of changes at once, this can be lost, and then you're trying to look which of the improvements destroyed your code. And if you optimize something, please documentate the changes for the maintainability. So this is, so I want with the talk that you have like a nice project experience and not be as like the second line of the XKCD comic that you're trying to overthinking your program or your code with the time scope of optimization and don't get further along with implementing features. So therefore, these are the key takeaways you should take away from the talk. Don't do micro-optimization, really focus on the bottlenecks. This is a little bit hard to discuss here in the talk because I cannot show like huge sums of code because it will be simply an overload. So also profile before your optimizations and focus on the bottlenecks. And this was like my talks. I'm finished and I'm happy for questions.
Yeah. So the first question was how to determine I/O, so disk speed, network speed, or database bottlenecks in Python. Do you have any recommendation for that?
Yeah, with external task managers, you can watch it, like watch the utilization with alarms. If you're in a cloud, you can use like alarms on the instances if like the disk or like the RAM is an issue. And then you can also look on the network traffic via Shark, and then you can see if this really is an issue and if you're really bottlenecked with that.
Mm-hmm. The next question was about the benchmark slide you showed in the beginning. It was how was the speed measured in the bar chart? What was the benchmark for that?
The benchmark was a snake game which uses a lot of list comprehension, dict comprehensions, and is built on different versions of Pythons. And yeah, this is a snake game. And the bar chart performance you see like on the right, like the 50,000, 100,000 is how many times like the snake simulation could run in each Python versions at given time.
Thank you. The next question was, how can you identify early on in your Python code you might have performance issues, even if it seems to be running smoothly, before you scale up?
This is really difficult because sometimes you are building your little script and you're trying on like a local PC and it works all right, and then you scale up and the performance completely breaks down. And to mitigate this issue is really test with real data, try to be close as the integration as possible. So then like the performance issue arises quickly. Yeah.
Mm-hmm. And then for a last question, before we wrap up, how would you decide if you have more I/O bound or more CPU bound problems? Do you have to use different profilers for that, or is it one profiler that combines everything?
As my knowledge, you need to use different profilers. So one for the network and also one for the CPU bound.
Thank you, and also thank you for your talk.